Not, well, I mean, I do, but it's mine for my lunch. So no, because it's mine. Come on, computer. My Google Slides is not recording. Hold on, I'm just having to hurry up and wait on Google Meet because it's having, there it goes, there it goes, there it goes. All right, well, I know you guys know the opener. If for some reason you missed yesterday, you did miss the Unit 11 test, which I believe is still open for right now. Should be through this evening. Let me unfreeze this. All right, for the opener, there are 3 subparticles of the atom. What are the 3 particles?
Proton.
The proton, neutron, and what's the other one? Electron. Okay, what is the charge of a proton?
Positive.
Positive. What's the charge of a neutron?
Negative.
No.
Oh, neutral.
Neutral. What's the charge of an electron?
Negative.
Negative. And where do you find them?
Outside.
Wait, which one?
The electron.
Okay, the electron is in the clouds. Okay, it's outside. And then where are the proton and the neutron located? In the nucleus, exactly. We're going to talk about what happens when those particles decide to go crazy and go through, there's Bailey, decay in some way, shape, or form. Get back on the right slide. All right, now, yeah, this is a bunch. I mean, it's a lot, and most of it is already filled in for you. I don't think I missed any of the blanks that I put into blue. Like, I need to follow along with this because, did I print these off? I hope I did. No, I did not print these off. I need to print these off. All right, so the nucleus of the atom, which where almost all of the matter is, okay, it's extremely dense, like extremely dense.
I knew it.
Okay,
I
so,
knew that was
and then this is, and I don't know how accurate this number is because I'm just pulling this from Azel's data share. But if you blew one nucleus up to the size of a marble, it's apparently going to weigh 250 million tons. A ton is 2,000 pounds, to put it in perspective. Okay, so 500 million pounds in the size of a marble. Now, I know it's not on here, but I know that if you took an atom and you blew it up to the size of like a basketball, and you went to a professional football stadium, and you stuck it like right on the 50-yard line in the middle, if that's nucleus, your electrons, that first set, they can only hold 2, are going to be outside of the stadium. And so most of, even though it's not on here, most of an atom is empty space. Okay, where the mass, most of it, yes, I know there's electrons, but most of the mass is located in the nucleus, and that's protons, and that is neutrons. This is the bulk of the answer to the opener. Protons are positively charged. Okay, neutrons are neutral. A neutron is what happens when stars do nuclear reactions and it fuses a proton and an electron. That is what a neutron is. That's why it's neutral. It's just a teensy bit bigger than a proton. Electrons are negatively charged. And in neutral elements, your protons and your electrons are the same. Okay. Now, well, I guess I should have moved that off on a different line, but I did not. And so in the nucleus, you've got your protons and your neutrons. Okay? And then in your electron cloud or ring or shell, it is cold. I'm gonna try to open it up one, but it's gonna make it hot. I don't know, that thing's possessed. It's just psycho. I forgot what I was saying. Oh, I totally went off track. I feel like my fingers are hurting. It's that cold in here. It's not normal. Maybe it broke. I don't know. I think it's cold in here. My hands are like ice. Oh, go back. But we are going to be talking about what happens when your nucleus essentially ruptures, okay? And it emits. It depends. It depends on the type of decay. Okay, there are 3 types. There's alphas, there's betas, and there's gammas. Now, this is going to take us a few days to get through. It has been literally a decade since I have done nuclear chemistry. I remember it now, going back over it. So your nucleus, those protons and those neutrons, a nuclear reactions that we do on this planet primarily use what's called alpha decay. Now there's three types. What's the matter?
Where are the things from?
Where are the thingies found? Protons and neutrons are found in the nucleus. Okay, electrons are outside in the rings. They're really not rings. They're really clouds, but bubbles. But normally when we draw one, this is your nucleus, and I'll just draw helium. We got 2 neutrons, 2 protons, and then in the first electron cloud, I've got 2 electrons. And so normally we draw these rings just because it's easier to draw a 2-dimensional thing on paper but they're actually 3-dimensional bubbles.
Protons, neutrons, and
Nucleus. Yes, protons are positive and neutrons have no charge, which is why I drew a 0 for no charge. The electrons are negative, which is why they get a minus. Now, these are not the smallest of the particles. Okay, it's not listed on here, but we have the Higgs, which we call the God particle. We've got different quarks. We've got taus, maus, gluons. And then we have like the quarks have different names. There's ups and downs. There's literally happies and sads. Like they seriously call things that. But we don't go that far into here. So what holds in the nucleus, if you think about magnets. If you put 2 positives next to each other with a magnet, what happens? They push away. So inside the nucleus, if you have just a bunch of positives and neutrals, magnetically, what is the nucleus going to try to do? If they're all the same charge? Push away. Okay, so blow up. Okay, but what keeps the nucleus from actually blowing up, which is how nuclear warheads work, they have this strong nuclear force, this binding energy that actually keeps them together. Now, there is such a thing as putting too much inside the nucleus, and which is basically radon, magic number 86, Rn. And when you put too much junk in this nuclear envelope, it can't hold it back. It's like putting too much water inside a water balloon. But what the binding energy does, okay, it's this glue that keeps those positives from repelling because magnetically, if there's positives, they want to repel. The binding energy, or what is called the strong nuclear force, keeps that from happening. I know that's not on here, but that is what it's called. Let's see, we don't have persons on here. Okay, so Veronica, you're online, Veronica, I'll get you in a second. Let's see, take this here. Lucas is here. So here, Sebastian's here. Caitlin's here. Logan, Jared. Reagan's online. Valerie is here. Reagan's here. Jeremiah. Okay. If I go too fast, let me know. It'll take most of this is already filled in for you. So if you put too many protons and neutrons inside the nucleus, it will be unstable. It will be what we call radioactive. It is going to try to lose some of the extras that are in the nucleus so that it doesn't want to blow up. Now, it's not, yeah, a nuclear warhead technically blows up, but it doesn't necessarily do it to give off a bunch of energy. Sometimes it's just a helium nucleus. But anything that is radioactive, radium, polonium, plutonium, curium, americium, radon, anything that has too much stuff in the nucleus will want to decay, and we call this radiation. Actually, we're doing this in the Earth space class right now too. We're talking about radioactive pollution, and we're talking about nuclear warheads, and nuclear power plants, and stuff like that. This was an accidental discovery. The Curies, Pierre and Marie Curie, they had a uranium salt, a rock that had uranium in it, and they put it on top of photographic paper, like the stuff that has to be developed, And they didn't know it was radioactive. They both died from radioactive sickness, which is a horrible way to die, but they did because they didn't know that what this stuff was. And when they took the rock away, the film was actually developed. And then they had to do a bunch of tests on it. And yeah, they both died a horrible death. Their teeth fell out, their fingernails fell off, their skin essentially they turned into a leper, and then they died a very painful, horrible death from radioactive sickness. Did I skip one?
I don't think I did.
The binding energy, let's see, what did I say on here? It keeps the protons from repelling. It keeps them from popping that nuclear envelope, this strong nuclear force. Okay. But yes, this was a complete and total accident, just like the Slinky. That was an accident too.
So it's good.
Was Play-Doh an accident?
Yes, it was
Really?
meant to be like stuff that you can paint on you.
Really?
Like glue, they said they came up. But then it didn't do that. And then his daughter started coming out.
And that was it. Now every kid plays with Play-Doh. I like the smell of Play-Doh. It reminds me of my childhood for some reason. It's weird how smells can do that. Did you get it? Can we go? Okay, sorry. But I swear, when I was doing these, because I have been building these this week. I did not get this done over the weekend like I normally do. So if I missed something, I'll highlight it. And like I said, if you missed yesterday's test, it is still open right now. There's, I believe, a 45-minute timer on it. So don't start it and then leave it or whatever. Oh man, my eyes are itching. Hold on. You'd think all that rain would wash that horse apple pollen out of the air, but apparently it's making more of itself. Ugh. All right. So when, like I said, when you put too much stuff, just like too much water in a water balloon, it essentially pops. It does not mean mushroom cloud. Okay. It can, but it does not necessarily mean that. And like I said, these things, is there one more? Yes, there is. It was an accidental discovery. Now you have 3 types of radioactivity. You have 2 types of nuclear reactions, which I think is not tomorrow. I think that's Friday when we do fusion and fission. I don't think that one's today. It is a lot of stuff that we are getting through on here. But radioactivity is just it's some type of substance that is not stable. It wants to lose part of itself to become more stable. So it's going to actually sometimes change into a different element. Sometimes it spits out a helium nucleus, which is this. Sometimes it spits out electrons. Sometimes it spits out pure energy. It just depends on what element is breaking down. Like, how is it spitting stuff out? And when I start showing you how to do the calculations, don't freak out, because that's what tomorrow's for. Making sure that you can run these things. What? You have to go right here. You guys cannot walk campus. They are watching the cameras. I will find out. It will come back to me, and I will write you up. You have to. I don't know. I don't know what happens, but the principals are extremely angry right now. I don't know. I do not know what happens. They don't tell us because of FERPA. Like I don't know. Somebody made somebody very, very, very angry. Well, they're taking it out on us too. That means it has to be something really bad if they're hammering the teachers, because they literally are watching the cameras to see which room you guys are leaving from, and they're coming down on us, which I don't like. We're so close to the end of school. All right, now when you have one of these 3 major types of things, okay, that are pushed outside of a nucleus, it's called decay. Now, I don't know if we're going to be able to get into half-life. We'll see if I can get in. Half-life's not hard. It's such an easy thing to calculate. But you have elements, depending on the type of decay. If they're losing protons, they're going to change elemental form, because the number of protons is what makes the element the element. And when you change these, whether you add or lose, in this case we're losing because we're decaying, we're breaking things off, you're going down by however many protons you've lost. So you need to be able to access the periodic table, because I know you haven't memorized that thing. And so why does radioactivity, why does it result in a different, that is not written well. What, did I copy it wrong? Why does a radioactive, why does radioactive, that is not grammatically correct. Anyways, I'll fix it later. Why does it make a new element? And it's because, like I said, it changes how many protons, and the number of protons is the same as the atomic number. The protons is what makes the element the element. Neutrons actually are sort of the super glue, the glue ons, the super glue that holds the nucleus together unless you just shove way too much stuff in the nucleus. And if it's neutral, the electrons are the same as the protons. When we did isotopes, you have different numbers of neutrons. When you have ions, you have different numbers of electrons. I honestly don't know what happened. I don't know if it's vaping. I don't know if it's kids having sex in the bathroom again. I don't know.
Wait, again?
Yeah,
So what happened?
that was why they were locked down. Like everything was locked down, what, like 2 months ago? At least that's what I was told. I don't even know any details. It's disgusting. But yeah, ew. It's just gross. All right, so I didn't animate this guy in, but it's no big deal.
Was it you?
Stop it. Shh.
Yes.
So isotopes, okay, those have different numbers of neutrons, but they're the same element. They don't have charges because the protons and the electrons are the same. It's the same element. It's just different numbers of neutrons. And that's why those atomic, not the number, but the mass, the bottom one, that's why they're not whole numbers. Because they average all of the isotopes by their weight composition and then they add them together, and that's the number that's underneath the symbol. Do what? Okay. I don't know. I mean, I thought, is it the parent portal?
Your student or the student.
So it's the same thing, but for you guys.
Yeah.
Okay. I was like, I don't know, I've only seen parent portal. All right, so if we're radioactive, like I said, they are unstable and they're gonna emit radiation. Now, you're gonna see things set up like this. X is the symbol for the element. And so like uranium is a capital U. Okay, A, and we've done this before, it's just been since first semester. A is the mass number, it's a whole number. It's your protons plus your neutrons. B is going to be the atomic number, which is the top number on the periodic table, and that's specifically your number of protons. We did this a long time ago. This is called isotope notation. So when you put the mass over the protons, this is the protons. If you subtracted them, it gives you the number of neutrons. And because isotopes have whole protons and neutrons, these are all whole numbers. There's not decimals. But yeah, this is what, the second 6 weeks of school?
Yeah.
Something like that. It was a long time ago. What is the symbol for an isotope of cobalt that has 33 neutrons? Did I do this on the next one or did I do it down here? Do you know what the symbol for cobalt is? CO. Okay, and so it has 33 neutrons. I have to look this up. So if I find cobalt, its atomic number is 27. Oh, well, this is reanimated. I gotta fix this. It's twice. Okay, so we're gonna do this one on the board. All right, those of you that are remote. This is cobalt. It has 27 protons. That does not change. That's the top number on the periodic table. Now, if I have 33 neutrons, what's 33 plus 27? 33 plus 27? 60. So that's how you would write cobalt's isotope notation. This specific isotope has 33. You add that to 27. So for those of you that are remote, letter X would be capital C, lowercase o. That's the symbol for cobalt. Letter A would be 60, and letter B would be 27. And once again, these will be whole numbers because these are isotopes of different elements that happen to be radioactive. Sorry, online people, it's not animated. Now, the three, okay, they are on here, three types. That is a lowercase a in Greek. It almost looks like a fish. Like, it's not like this. It's like almost like the infinity sign, but not finished. An alpha particle is a helium nucleus. Okay? This is the weakest of the three. You actually can put up a force field of paper and I could shoot alpha particles at you and they would not get through the paper. Okay? But they are still a type of radiation. No, but I said if I could. If I could. All right, so the symbol, because it's a helium nucleus, He, it is 2 protons and it is 2 neutrons. So the top number is 4. Okay, the atomic number of helium is 2. This is how we represent an alpha particle. That's what it is. That's all it is. Now, very, very big elements are going to go alpha decay. This is what we're going to be spending our time on tomorrow, is how did I do this? Okay, so this is californium. Okay, it is not stable. It has way too much stuff in its nucleus. It's going to break down to, which one's CM? Curium. It's going to reduce by a mass of 4. 4 plus 247 is 251. Okay, and then it's going to reduce the number of protons by 2. And so 98 minus 2 is 96. When I look up 96, I just had to double check it. That's when it was curium. Yeah, curium. Okay, so CF is the parent element. This is what we're starting from. It's going to produce a daughter element. I'm sorry, there are no son elements. They're not being sexist. It's just what these are. They're not, I swear. So the symbol for the daughter, now this is the alpha decay. You're going to have the symbol for the new element, which just subtract 2 from the atomic number, and you're going to subtract 4 from the mass, whatever it was, and that's going to be the mass of the new isotope. And it says over on the right, it says found by looking at the bottom, that means the bottom number. Is that not the helium, this one, the 96. And yeah, you still need periodic tables, because I know you have not memorized them. So you have the parent, californium, you've got the daughter, curium. And so we're going to see if you guys can do one here real quick. PT is plutonium, right? No, platinum is PT. I'm going to figure out what element is here. Okay, so I know I need to subtract by 2. And so which atomic number am I looking at?
76.
76. So when I look up 76, it's osmium, which is OS. So 78 minus 2 is 76. 190 minus 4, what's the top number going to be?
186.
186. Oh, why did I put a 60? Oh, I made a boo-boo.
Oh, that's cobalt.
No, I made a boo-boo. Let me fix it. Yeah, that's cobalt. Oh, you guys have a different one up top, don't you? I made a boo-boo transferring it over. Hold on. Oh, I don't know what I did. Okay, I'm gonna skip down here because this is the right one. I did something wrong. I wonder if it was the new isotopes of daughter molecules. I don't know what I did. I don't know where I got that one from. I'm gonna yank that out of the thing. Okay, so this is the right one. Who knows? Who knows what the heck I did? All right, so we knew, we said it was 186 and it was 76. And then the symbol is OS. I don't have the slightest clue how I did that. That's what I get for not double checking it. I don't know where it came from. Oh, What was the symbol for the isotope of cobalt that has 33 neutrons? I put it in the wrong spot. The stuff I did on the board, I was trying to do there, and I didn't pay attention when I was putting stuff over. So anyways, in alpha decay, I'll fix that. In alpha decay, you subtract 4 from the top number, and you subtract 2 from the bottom number. You look that one up to get its symbol. And so platinum is the parent, and osmium would be the daughter. All right, next one, beta. This is also a Greek letter. It's a capital B that starts off with a tail like this. With lots of Greek in radiation. This is a negatively charged electron. This is a little bit more powerful. Now, it says in the notes that you can stop it with wood, but you can also stop it with a thin sheet of aluminum foil. So like the people that wear the aluminum foil hats so the aliens can't get into their brain, you can't shoot them with electrons because it'll stop it. Not that you can have an electron gun. Why is it not going forward? There we go. So if we have too many neutrons, you have an electron that's emitted. So the bottom number, you're going to add one, but that doesn't change mass because electrons technically have mass. Let's hope I didn't mess this one up. They technically have mass, but it's 1,180th that of a proton. So it's so much smaller that it doesn't really change the mass because it's negligible. So TB is 65. I gotta find it. Thank you. Terbium. Like I said, I don't memorize all of them. We're removing an electron, so instead of it being 65, it's going to be 66. Top number does not change. Good, I didn't mess this one up. And so if I find 66, dysprosium. If I don't hold it right, I can't read it with my glasses. That's dy. Okay, so the previous one, alpha, okay, you take away 4 from the top, you take away 2 from the bottom, you look up the bottom number no matter what. Okay, alphas are the weakest of the 3. It is still radiation. Alpha is the weakest of the 3. You can stop it with paper. Beta is essentially an emitted electron. Okay, this is stronger. This is the middle power grade, if you will. You can stop it with, it says wood, but yes, you can also stop it with thin sheets of aluminum foil. You are adding 1 to the bottom number. The top number does not change. You still look up the bottom number for the symbol of the element. This is how we represent beta decay. Helium decay is He with a 4 on the top and a 2 on the bottom. Gamma, great, that's not. I can't get the Google Slides. Why is it not going? What is going on here? Why are you not going forward? Animated, way out of order. What the heck, you don't do on this one? Why is that not going? I don't know what I did. Let me go through. It's like it's animating and nothing's happening. There we go. In gamma radiation, now this is not written properly in Greek. It should be okay on yours where it sort of looks like that. I can't get the Google Slides to do that. So it looks similar to a Y. It's got 2 zeros on the left. This is pure energy. This is the bad one. This is the one that you have to have like 4 inches thick of lead or multiple thick feet of concrete to stop. This is the bad stuff. This is what happens with nuclear reactors. So in this case, I have neptunium, 93. Yes, neptunium, named for Neptune. And so you don't change. That's not right either. Is it on your paper this way? Oh, sorry. This is what I get for not checking this. Is it on your paper that way? This is supposed to be yellow. Let me fix it too. I'm gonna have to re-record this in the other class. This is a 0. This is a Y. No, this is not right. Did I do the sample problem? I am gonna have to totally jack these things around and fix it. Oh, I'm sorry. No, I did do this right. I didn't read it right. Okay, so this is it. I did it right. Okay, so if you have to figure out which type of decay is going on here. This was not the example for the gamma radiation. That's two slides up. So if you are going up by 1, even though I just had the answer, but this does not change. This is an example of beta decay. Let me go back to this. I really should have started this on a new slide and not left this with gamma. Okay, so because I'm going up 1, this is the electron one, this is beta decay. The second one, and there we go. Now uranium. If these numbers don't change, is it alpha, beta, or gamma? Gamma, which is the Y with the 2 zeros. Okay, and then if you change by 2 protons, that should be that's got a problem too. Well, you tell me, what did I do wrong on the alpha? This is okay. What's wrong with this?
It should be 6.
Yeah, it should be 216. I am going to re-record these and put this back up because there's too many things that are wrong on here. Okay, so if I go back to this one, we knew that this was beta decay because we went up by 1 with the protons. Okay, and then if I go, since this is so jacked up, if I don't change, this is gamma radiation. And then this was the error that I had. If you have the change of 4 with the mass and then a change of 2 with the atomic number, that'll be alpha decay. I know that the next thing is animated right because I checked it this morning. All right, we're gonna fill in this chart. Too many errors. This is what happens when I don't get this done over the weekend. Gosh darn it, I went and had fun for Mother's Day. All right, so alpha, well, that's what happened, honestly. I didn't spend my entire weekend doing schoolwork. So what are the numbers for a helium nucleus? What numbers go here? No, 4 and 2. This is how you represent an alpha radiation particle. It is a helium nucleus. What is the total mass of an alpha particle? 4. Now, how many protons are in a helium nucleus? 2. So in the nucleus, you're going to reduce by both 2 protons and 2 neutrons. So the negative just means you're going to take them away from the parent. This has the least amount of danger. It is still radioactive. If you are exposed to enough of any type of nuclear decay, you will get radiation sickness. You will die from it. It's not ulcers all over your body. Like I said, teeth and fingernails and hair falling out. It's not a good way to die. And then what will stop this one? No, well, that will too, but you don't need something that strong. This one you can literally stop with a sheet of paper. Beta, this is the electron, okay? You are 0 and -1, so you actually have an increase. With the helium, you have a decrease of 2 for the element. With a beta, you have an increase of 1. And when I say increase and decrease, I mean the atomic number, the top number. This has essentially the mass of 0. It is equal to the mass of an electron, but it's so tiny that we sort of ignore it. So we have, technically, it does have mass. Okay, it's whatever 1/1170 is, whatever that is. It does not change the nucleus. No, it does change the nucleus. It adds a proton. Another typo. Another typo. Proton. Plus 1 proton. Let me go back to that. I just need to stop the recording right now because I'm not putting this, there's too many errors. This has a medium danger. Like I said, all radiation is still nasty, but you can stop it. The note said void. I always taught aluminum foil. And then the last one, gamma, this is the Y with the 2 zeros. This is pure energy. Okay, this is what the sun gives off. This is what the magnetosphere protects us from, so we have the wonderful atmosphere that we can breathe, or we die. You get a big enough solar flare slamming into the magnetosphere, bye-bye, and it literally radiates the oxygen and nitrogen gas that's in the air that we breathe, and it escapes Earth's gravitational pull, and it's gone. Kills life on the surface of the planet. This does not change the nucleus at all. This has the highest level of danger. And you're going to need either lead or concrete to stop this problem. This is why nuclear reactors have like 13 feet thick of concrete around the core. So that, you know, the people that work in the power plants don't die. But this sort of puts everything together. Now, you have something that is not this math as the assignment. And there's a link in Canvas that goes through, let's take a look at this nuclear gallery thing. I told you this was going to take us the bulk of the period. There are a bunch of different things, like good and bad things, that have happened with nuclear radiation. And it wants to know what happens, when did it happen, or when was it discovered, where did it happen, or where is it being used. You don't have to give me paragraphs in here, so a fact about what was going on. And is it a positive, is it a pro or a con? This is going to take a while. We have tomorrow, if you do not get this finished, to work on this, but we also have tomorrow to do these. So figuring out what's going on, is it alpha, beta, gamma? And what is the new substance that is created with?
Tomorrow.
It's to do that, okay, but also to do this. It's making sure you understand which one's which, even though this thing was just chock full of typos and stuff. I'll go back and I'll make sure that I re-record this. Well, it's technically this one is today and that one is tomorrow. I know.
6 minutes.
I know. That's why I'm giving you tomorrow to be able to work on both of them. It goes with it. Stop complaining.
I'm going to complain because I don't
So,
think.
I don't think we have to do is compare.
Once